this is me. This is what I do for a living. I do a fair amount of consultancy work, and that consultancy work has led me to use Monte Carlo simulations a great deal. And as I said in the blurb, most people who do data science have their own favorite set of things they like to use. And I like Monte Carlo simulations a lot, and that makes me biased in favor of them, obviously. On the other hand, I'm biased in favor of them because I use them a lot, so it's kind of recursive. They don't solve all known problems, but they are very, very useful, I think, anyway. So a Monte Carlo simulation is a way to mimic some aspect of real life in a computer model. So they're for modeling what goes on in the real world. What makes them interesting, in one sense, is that they use random numbers. And most or other simulations don't, Monte Carlos do. Why you use random numbers and why they're important and why Monte Carlos are good is, I think, best illustrated by an example, and I'm going to give you a couple of examples. The example that I'm going to use first is the one that caused the invention of Monte Carlo simulations, which is quite a good way of thinking about it. So a guy called Stanislaw Ullmann in 1946. If I tell you he was a physicist and he was at Los Alamos at the time, you can probably guess what he was doing. He was working on the atomic bomb. And he was in hospital, and he was bored out of his skull because his brain wasn't injured. I'm not sure what he was in hospital for, but he was playing Monte Carlo. He was playing what is called Canfield solitaire, what the Americans call solitaire, what we call patience. And he was dealing out a pack of cards. And Canfield solitaire is interesting in that it's very mechanistic. You deal the cards, you play by the rules, and either it comes out or it doesn't. You know, you play by the rules, you get it out or not. And he fell to wondering how likely it was to come out. And he started doing the combinatorial combinations. So, okay, I'm going to lay out the cards. There is a 1 in 52 chance that this is a king. There is a 1 in 51 chance, that, and so on. Sorry, 4 in 52 that it's a king, I beg your pardon. So he started doing the combinational or combinatorial calculations for that. I would ask, can anybody see the flaw in that? And he very rapidly could see the flaw. They are mind-bogglingly complicated, way too complicated to actually do, and certainly not lying on your back in a hospital bed. But the epiphany he had was that he could not sit and do the probability calculations. What he could do was play a couple of hundred games and count how often it comes out. And lo and behold, that would give him a good estimate as to how likely it was to come out. And the more games he played, the more likely he was to get a more accurate answer. So if you play one game, either you get 100% it comes out or 100% it doesn't. That's not much use. You play 10 games, if the chance of it coming out are 70-30, you might get 5-5, you might get 8-2, you might get 7-3. The more games you play, the more likely you are to get the right answer. And there are a couple of slides here because this sounds almost like a fairy story, like it didn't really happen, or that it's been simplified. So these are Stanislaw Ullmann's own words as he wrote about it. So this is not a fairy story. He really was lying there trying to work all this out. And what he realized was that this wasn't just about playing solitaire. That was trivial. He realized that there were lots of problems they were working on with atomic weapons, like, for example, how rapidly one material will diffuse into another. Well, that diffusion process has a whole load of random steps. But in the end, you can either try and do the probability calculations, which were crippling their work, or you can run a Monte Carlo simulation. You can run it thousands of times and see what the end result is. So, and they also realized even at that point that they could use computers for this, because you don't have to use computers for Monte Carlo simulations. They're just very good at it. So they published a paper in 1949, and this is where this system was named. For those of you interested in these things, it's quite clear Monte Carlo simulations were being used earlier than this. And I kind of put on a slide somewhere, I think this is where they were named. I don't think they were the first people to think of the idea. They were the first people to write a scientific paper and name it. And it's called the Monte Carlo method primarily after the fact that it's to do with probability and random numbers and gambling, and Monte Carlo was a famous place to gamble. So I don't want to show you a solution for Canfield solitaire. It's been done. Some place where I have used them is to do with random walks. So for those of you who don't know, and I apologize if you all do, a random walk is simply, the idea is you're put down in the desert and you're trying to get out. And you adopt a really dumb strategy for getting out of there. You decide to walk at random, either north, east, south, or west. You take one step and you randomly decide again to go north, east, south, or west. So you might go north, east, east, west, north, south, south, east. That's a random. Now, in the 1930s, physicists were very, very, very interested in solving the problem. And there's quite a few problems associated with the random walks, one of which is after n steps, how far away are you on average from your starting point? So if you take 100 steps, on average, how far are you away? Now, clearly, you could be, in theory, 100 steps away, because you could go north, 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 north. That's unlikely, but possible. You could end up exactly where you started. And the answer then to this, how far away on average will you be after 100 steps, has to be between 0 and 100. But where is it? And if I tell you, well, I've shown you there, Einstein worked on this problem. He was fascinated by this and he worked on it. So we are talking about an Einstein level problem here. We're not talking about a trivial problem to solve. And Einstein, amongst others or with others, proved that the answer is you are the square root of n steps away on average. So I chose 100 for a good reason. If you walk 100 steps, on average, you are the square root of 100, which is 10 steps away. And Einstein proved that. Now, Einstein was a very great mathematician. I am rather a poor mathematician. I could no way prove it, and I probably couldn't understand Einstein's proof either. But I can still solve the problem. And I will solve it, well, you've guessed, surprisingly, with a Monte Carlo simulation. I will simply write a block of code where somebody starts at point 0, 0, and the computer program chooses a direction at random, north, east, south, or west, and they walk that. Then it chooses another step, north, east, south, or west, west. You do that for 100 steps, and you measure the linear distance from the start point to where they are. Now, the first time you might get 23, the next time you might get 3, the next time you might get 8. You do it enough, and that number will centralize down to the correct number. That's what a Monte Carlo simulation does, and it's a nice illustration of it. When I started teaching people about Monte Carlo simulations, which was a long time ago, I couldn't find anybody who'd ever kind of spelt out the basic rules that you use over and over again in a Monte Carlo. So what you do is you do this list. Now, I'm not going to read it to you because I'm going to show you that with the random walk solution in it. But these are the steps that generally you follow when you're doing a Monte Carlo. I wouldn't make it completely prescriptive, like you have to follow these. I'm just saying mostly you do. So, okay, if you're going to try and do this random walk, how far will a random walk take you after n steps? Question is, what's the domain of values? Well, the answer is this. The domain of values, the set of values you're going to draw for, we've decided are north, east, south, and west. Now, you can expand that. You could make it north, northeast, east, southeast, south. You could make it 8. You can make it 360. But you choose the domain of values. You draw from that domain. Well, I'm drawing at 0.25 for each of them. I'm not biased in any direction. I have an equal probability of choosing north or east or south or west. What I then do is walk that person for 100 steps or however many I want. I measure the linear distance from the origin, and then I do that 1,000 times, 10,000 times, as often as I want to, and I get the answer. So if we do that, that is a block of R code. I mean, I wrote it quite a long time ago, and nowadays I'd probably write it in Python, but it doesn't matter. It's fairly, I hope, clear that the code is short. I don't expect you to kind of read this and understand it, although you may be good enough to do that. But what I do want to do, sorry, is obviously not push that button. I want to just show you this running in R. So there's the code. You'll see that it's saying, okay, we've got 4 possible directions. We're going to take 100 steps. We increment the steps. We're going to run this simulation 50,000 times and average that. That's the code. If you run it, faster machine now than when I wrote this, the answer is 8.86. You're thinking, well, that's wrong. No. Einstein got square root of n. Obviously, I'm smarter than Einstein. No, nobody believed that. No, I didn't believe it either. The answer is that this is a very simple model of a random walk, and we are walking only north, east, south, or west. The one Einstein solved allowed you to walk in any direction. And you get this faint compression of the distance if you restrict it like this. So the answer is I'm solving a slightly different problem from the one Einstein solved. Okay, I could just make this more detailed. I can put 360 steps up there in the starting steps. But I wanted to keep the code as small and readable and understandable as possible. One other thing that I can do is I can run this code again. So we got 8.86, 8.87, 8.87. You'll see that it's reasonably reproducible. And that gives me some degree of faith that I'm running it enough times. If I chop this down to, instead of 50,000 times, 5 times, and run that code again, what I'll get is a much more variable answer, 9.48, 9.68, 9.96, 10.33, 6.3. It's quite variable. If you get a variable result, just increase the number of times you're running it until you get a stable number. So it's a good kind of trick with Monte Carlo simulations. If you want to know if you've run it enough, just try it. Purely for fun. I mean, I know we don't program for fun, we do it for seriousness, but I couldn't resist actually drawing the walk. So this is one walk. This is one walk of 10,000 steps. There's the origin, there's the end point, and look at the interesting pattern that person walked over. And this is a bit compelling after a while. And I have no idea why, but it often looks like continents on a map if you do this. You get these areas of quite intense walking and areas where there is no walking at all. The other thing that becomes compulsive after a while is you keep on running it just one more time because you want to see how close you can get those. I mean, this can go on for hours, or how far away you can get them. So you can have fun with these, and I think fun's quite a good thing. So let me just get back to the correct place in the slides.
And Mark, just whilst you do that, so there's a question on.
And I've included the code in there,
Sure.
just in case anyone wants to play with that. So I'm just trying to get to the stage where I can also see you guys. Sorry about this.
So can you hear me, Mark?
There we go. So apologies, as I said, this is not my normal machine. Okay, there's another plot. there that I didn't show you, which is the plot. Here you can see along here you've got the number of steps that are being taken, and this is the linear distance from the origin. So you're seeing this as it goes along. So here this guy is walking away, going a long way away, and then ambling back towards the origin. Now do bear in mind this is only simply the linear distance from the origin. So you can do one simulation, and that's for whatever that is, 100,000 steps. So interesting. You can do that simulation again and again, and you can do multiple simulations, as I've done here. The other thing you can do is run 20 simulations and average the position. And note what's happening. It's kind of what you'd expect. These guys are all quite variable. This guy is smoothed out already. And you think, well, yeah, but Mark, oh, well, the other thing we can plot in is Einstein's prediction. And it just looks as if I get close to it. But the question is, why are you averaging 20? I mean, why average 20? Are you mad? Average 50,000. Now, by the time you run this simulation 50,000 times and average at each step how far you've got, you get this beautiful smooth curve. And again, you can see this disparity between what I think and what Einstein thinks. And trust me, you need to believe Einstein. The guy was as smart as they say. I think. I've never met him, but as soon as you see a curve, if you're working on a simulation and you see a line like that, just run more. When you see a curve like that, I don't think there's much point in running the simulation for longer than that. Okay. Does my answer sound reasonable? Well, actually, I think for a 4-step process, northeast, southwest, it does look convincing, and I'm fairly convinced that's the right answer. But a crucial point to remember about this is not a proof. What Einstein did was produce a mathematical proof, which is the end of the discussion, particularly if you're Einstein. What a Monte Carlo simulation does is give you an empirical answer. And it might, for example, be a much better match to the square root of n minus 1. I didn't work it out logically. I work it out by just seeing what the end result is. But very often, particularly in the commercial world, what the business wants is an answer to this question now. And they don't want it proved. They just want to know what the answer is. And this is where Monte Carlo simulations come into their own. They are very, very good at giving you a very close approximation very quickly. And in the business world, often that is what people want. Sorry, I've got to just move this lot around again.
Mark, can you hear me?
Not this. Don't do this on my own machine. Or I don't have to do it on my own machine would be a better way of putting it. Okay, so now they're highly applicable, and I teach this course in data science, and a lot of my students, well, all my students are very bright because they're my students. We also have a Slack channel on which we communicate, and one of my ex-students, Paddy Blackwell, posted this problem only about 3 or 4 days ago. And you can look it up. That URL will take you to the police publication of this case. It's an unsolved case, and a body was found in 1990. So it's a long time ago, essentially a cold case. And in the pocket was 53 pence worth of change. And that site doesn't tell you, and we're actually trying to find out, what the mix of coinage was in that. But there were 53 pence, so it might have been 50 pence piece and 3 pennies. It might have been 106 halfpennies, as existed in those days. But the interesting thing was the dates range from 1967 to 1975. The body was very decomposed. It was a skeleton by the time it was found in 1990. So one of the things the police were interested in doing was putting a specific probability of that person dying in different years, or the body ending up there in different years. Now, clearly, it's very, very, very unlikely to be prior to 1975, because that would imply somebody was planting coins on the body, which is unlikely. So it looks like it was 1975, but that's then a very interesting question. If we all pulled out the coins out of our pockets and looked at them now, it's very highly unlikely we will all have a coin from this current year. We will have coins from a couple of years ago, 3 years ago, 5 years ago. So the question is, can you assign probabilities, the probability to different years? And the answer to that is, of course, yes, you can. And if we assume no coins are planted on the body, we can make these estimates. And the more information we have, the better model we can build. And clearly, you know where I'm going with this, that the easiest way of doing this is Monte Carlo simulation. You build a pool of coins that represents the coins that were in circulation in 1975, the set that were in circulation in 1976, 77, 78, 79, 80, all the way up to 1990, although the body was pretty decomposed by then, so it's probably not 1990. But for each year, you build a pool of coins that represent the distribution, and then you draw the specific coins that were found in the pocket, and you see what dates you get. And you will get a range of dates, but for each year, you will get the highest probability, the distribution of coins. You match that to the highest probability for the year, and you have the best estimate you can. And the more information you can get, the better. And we've been talking to the Royal Mint. As it happens, I know somebody in the Royal Mint, and we've been asked, they are happy to give us, and in fact, they publish a list of the mintages, each year, how many of each coin is minted. So that's quite good information. What we don't know is how many coins are pulled back from circulation, and that would be helpful to know. But this is just a classic example of where you can use a Monte Carlo simulation. It is much, much easier to do that than to try and calculate the probabilities. So again, you can say, well, how does this fit into your pattern mark of Monte Carlo simulations? You define a domain of possible inputs, which is for a given year, say 1980, you define the pool set that would have been around at that time. If he had 5 coins in his pocket, we don't know that yet, but you draw the number of coins from that pool, and you can match the denomination of the coin to the number of those coins. You say, are any coins later than 1975? Yes and no. And you calculate the percentages of yes from, say, 100,000 draws. And that tells you the probability of it not being in that year, because anything beyond 1975, or you can calculate the percentage no. It doesn't matter which one you calculate. It's telling you how likely it was that he died in that year. So I was chatting to Paddy on Slack, and in typical Paddy fashion, because he loves problems, as all good data scientists do, he's actually written a Monte Carlo simulation to try and solve this. And he'd written it before I told him I was giving this talk and asked him if I could talk about it. And he's very happy to share the code. So that's a pointer to the code, and you are more than welcome to copies of these slides as soon as the talk's finished. So that's where you can look up this code. Just to give you an example of it, that's some of the code. That's one of the functions he'd written. But it's doing exactly what I've been talking about as a Monte Carlo simulation. That's what it is. So those are a couple of use cases. Other things, and I hope they give you enough of an idea as to what a Monte Carlo simulation is used for to be useful. Having said that, I found Monte Carlo simulations very useful for reverse engineering things. And if you look at the usage of Monte Carlo simulations in the commercial world, they are very heavily used in the finance industry. You walk into a financial place, you talk about Monte Carlos, they know exactly what you're talking about. To my surprise, they're not used in a lot of other places where I will use them anywhere, oil and gas, insurance, anywhere. But what a lot of people don't seem to have cottoned on to is that you can use them to kind of reverse engineer reality. Let me give you an example of that, because I think that is very, very useful. Suppose you have some process, so I'm finding it difficult to draw on this as well. That was supposed to be a rectangle. Even I can see that doesn't look like a rectangle. Okay, so we have a rectangle, which is some form of process. And we don't know what the input into that. Say you've got two inputs, A and B, into that. And we've got output C. Now, just to make this slightly more realistic, that might be, say, a website. And the input that we don't know are, let's say, the gender of the person and their income. Doesn't really matter what it is, but you've got people visiting the website. You've got their behavior on the website. But you don't know how many are male and female, and you don't know their income bracket. Well, what do you do? Well, one thing you can do is to build a Monte Carlo simulation of this web page with the information that you have and that you think appertains here. So you might think that females, and you might have evidence for this, tend to buy specific products on here. You know, product Z and product B tend to be bought by females. Q and R tend to be bought by males. People with high income tend to buy product P and Z, and people with low income tend to buy product 3 and 4. You can build a model like that. You can feed in a gender ratio here of maybe 60-40 and an income distribution. You might have more than one income level, A, B, C, D, and you might feed in 20% of those, 20% of those, 20% of those, and 40% of those. You feed those in, you know how males and females behave, or you think you do, you know how income brackets behave, and you look at the behavior that comes out of your model. And guess what? It's nothing like the reality that you get. Well, okay. Why is it not like the reality? There are two possibilities. One is your model is rubbish, so you've got a rubbish model. And the other is that you're feeding in the wrong ratios here. Now, if you believe your model is good, and sometimes we have very good evidence from other websites about exactly how these groups behave, we can tweak. If we think it is a good model, and we can often build quite good models, what we do is we tweak the inputs until we get the correct behavior. That is, we get the behavior that matches reality. Now, this works really well, and that can easily become more complex than this. You can have 3 or 4 inputs, in which case you are essentially playing a Monte Carlo simulation of a Monte Carlo simulation, because you'll feed in a set of parameters here, look at the answer, feed in a different set, but you can write a program that just feeds those in. It's not really a Monte Carlo of a Monte Carlo. This is definitely a Monte Carlo simulation, because this isn't using random numbers. But what you're doing is throwing in very large numbers of inputs. And the interesting thing is you may find that a set of inputs where, you know, gender ratio is 60-40 and A, B, C, and D are 20-20, 20-40. And that may give you a very close match to that behavior that you see. But you may find a completely different set here. You might find 397 and a different set of A, B, C, and D values. So you have to be slightly careful. Just because you find a good match doesn't mean it's the only good match. There's a kind of distribution going on, and you're looking for high spots, which are the high matches. It's worth mapping the entire area, because you may find multiple high spots. Then you have to do some work to try and differentiate between those. Nevertheless, kind of reverse engineering with the Monte Carlo, where you know what the answer is and you want to know what the inputs are. As long as you can build a good model, you can do that. There's absolutely no reason why you shouldn't. And that has proved to be extremely useful for me in the work I've done. Okay, and now a complete non sequitur. Why is a gas-powered fridge like a random walk? And I know you're all trying to answer this. You're all trying to type in the answer as soon as possible because you all know. This is a little factoid I just happened upon purely by chance. And the connection between those two is Einstein. Einstein worked on both random walks and the gas-powered fridge. And in fact, Einstein, along with Leo, I don't know how to pronounce this guy's second name, Szilard, don't know. But those two guys hold the patent on the gas-powered fridge. And Einstein is always remembered for being very, very mathematical, with very good reason. He was also immensely practical. I mean, he was good at thinking about mechanical and thermodynamic problems. So I don't know if any of you have ever seen a gas-powered fridge. They're terrifying devices. I lived in a flat with one. And you walk in, you turn the gas to the fridge, you strike a match and you light a little, tiny little light at the back, a little flame. And as long as that burns, the fridge remains cold. I say it's terrifying because this was the 1970s, I'm very old. And when you opened the back door of the flat, if the wind was blowing, it blew the light out. But there was no cutoff at all, so it just went on generating gas. And you knew that the flame had blown out when you opened the kitchen door and it was full of gas. So I don't think Einstein designed a safety cutout on this. That's potentially a mistake. And I think this is why you don't see them anymore. I think all the installed ones have blown up by now and it's gone. But that's the connection. And I make the point only because I think Einstein is, you know, he's Einstein. I mean, the word means genius, but he was a genius in far more ways than people actually, I think. Galton's quincunx. Some of you will be familiar with this, some of you won't. If you haven't seen it, it is a fascinating device. And it is essentially a Monte Carlo simulation, but made out of physical things. And if you haven't seen it, balls drop and they hit a rod and they bounce either to the left or to the right, and that should be 50-50. And it is a perfect Monte Carlo simulation as a physical device. And there used to be one in the Boston Museum of Science, which was huge. It was like 20 feet tall. And they used to set it off once an hour. And you could hear this thing all over the museum. And I waited for about 3/4 of an hour just to see it. Because I'd seen them before, but nothing that size. So I really would recommend, if you haven't seen one, have a play with it. And what it also teaches you is a very important point, which is where normal distributions come from. So it serves about 4 purposes, that. Okay, so we're perfectly on time because we get to the end of that. And the 2 other terms I want to introduce you to, and again, I'm perfectly well aware that a lot of you may know these terms, and I apologize, but deterministic and stochastic. And these are 2 very good terms to do with Monte Carlos, because Monte Carlos are stochastic. They are not deterministic. But it's worth covering what those 2 terms mean. And also, as a sideline, I can introduce you to this wonderful thing called the expected payoff, which I think is really useful. So this is not going to be a Monte Carlo simulation, incidentally. We're not going to solve it that way. We will solve this problem with the expected payoff. So suppose we work for a company, sells insurance by phone. So we have existing customers, they bought insurance from us before. We have a team who ring them up and try and sell them a new insurance policy at the end of that one. And we have written a system which does real-time analytics on the call. That is, they ring up the person, hello, Mr. Smith, how are you? Have you had a good time? Yeah, I know, COVID. Oh, tell me about it. Yeah. So you have a conversation and then they say, right, do you want to renew your car insurance? Because we've got some great deals for you. And you talk to the person. And all the way through, a real-time analytical system is running on that. It's listening to the answers to specific questions. It's also listening to their word usage, and it's listening to the nuance. Times have been really hard. We've been really suffering financially. Well, you're not going to try and sell that person a very expensive policy, or you're a hero if you can, because they're not going to buy it. So it listens to the answers to the questions, the word usage, and the voice pattern. How relaxed is this person? How chatty are they? How annoyed are they? How annoyed they're getting? Are they more annoyed now than they were at the start of the call? And you will gather I'm describing a real system to you, but we won't name names. So on the basis of that data, the analytical system looks at 3 products that you can sell them, product A, B, and C. And it assigns a probability that that customer will accept it. Now, none of this is a Monte Carlo simulation. This is just analytics. And it turns out the probability, if you offer them A, the system is predicting there's a 14% chance they'll accept it. If you offer them B, that's the most likely one they'll accept, which is 54. C has a lower probability, 32. Now, I think intuitively, all of us can see you're not going to offer them product A. It makes very little money for you and they're not likely to accept it. So that's an easy decision. But of these next 2, it's harder because product B is the most likely one they will accept. So that's good, but you only make 90 quid from it. C, they're less likely to accept, but you make a lot more money. So the answer is, how do you decide between those 2? And this is a thing, it's a very simple calculation, painfully simple. It's called the expected payoff. And you simply multiply the payoff you're going to get times the probability of it working, and whichever is the biggest number, that's the one you take. And the clear winner here is C. They'll only accept it 1/3 of the time, but you make enough extra money from that for it to be worthwhile. And gamblers have known about this expectation or expected payoff for a very long time. And this is a fairly well understood principle. And that's why I was saying, I'm sure a lot of you know about it. But if you don't know about it, it's very useful. Very, very easy calculation to do. It certainly was known in Blaise Pascal's time. And Blaise Pascal famously applied the logic to belief in a deity. He said that either you believe in the existence of a deity or you don't, or you're somewhere on a spectrum between those 2, 0 and 100. However, if a deity exists, the payoff is infinite because you will spend the rest of eternity in heaven if you believe in the deity and you live by the deity's rules. And Blaise Pascal said, it doesn't matter what payment you have to make in this life, no matter how much effort you have to put in, the payback is infinite, and one number times the other is infinite. That has to be more than not believing in the deity. So that was why he believed in God, which I think is a logician's perfect answer. What's my point about this? My point about this is that calculations like this, like the expected payoff, are what are called deterministic. And that means simply that when you do the sum, you get the same answer. And every time you do the sum, you get the same answer. You can do it next week. You will get the same answer. It is determined by the process you're using. You take this number, multiply it by that number, and you get an answer. That's deterministic. The opposite of deterministic is stochastic. And stochastic is a process where you run it once, you get an answer. You run it again, you're actually unlikely to get the same answer. And that's exactly what happens in a Monte Carlo simulation. You do the random walk, you end up 5 steps away. You do it again, you end up 65 steps away. You don't know what the answer is when you start running the system. And Monte Carlo simulations are stochastic by definition, because we use random numbers. I think it's A, just useful to know, but B, I think it's a glorious word. I mean, it's just a nice word, isn't it? Stochastic. Now that rain sounds slightly stochastic to me. Anybody fancy a pint of stochastic? I mean, you can use this term in a whole lot of different ways, but it's a useful term to know, I think. So that's stochastic. That's it. That's Monte Carlo simulations.